I'm happy to present Jana Mareckova on stage. She's assistant professor from University of St. Gallen. So, Jana.
So the title of this talk, Unmasking Unfair Correlation, will focus on a slightly different aspect of labor market that is very interesting for economists. So, and in particular, the focus will be on evaluation of effective programs for unemployed individuals. This is a very interesting problem from many aspects. One of them is that there are many different programs to which these individuals can be assigned to. And there are also many different outcomes based on which the effectiveness of these programs can be evaluated, for example, future probability of employment or future level of earnings. So the framework in which we can do such an evaluation analysis is called potential outcome framework, where we capture the following data about unemployed individuals. So the first, we have the vector X, containing the features, the information of all unemployed individuals. Then we have the variable D, which codes the treatment, or in other words, the program into which the unemployed person was assigned to. So if an unemployed individual did not go to any program, this is typically coded as 0, and then we call this group of individuals control group. If the unemployed individual attained a program, then some non-zero value labels the program the person attended. Now comes a very important element, which is called the potential outcome that gave the name to the framework. And the potential outcome, here denoted as YD, captures what would be the outcome, for example, the probability of employment or the level of earnings, if the unemployed individual went to this program D. Now, this framework opens doors to the following parameters of interest. So a very standard classical parameter of interest is the first one, the average treatment effect, where we look at the expectation. So E stands for the expectation. So what we expect to happen on average in the population of all the unemployed if we would look at the difference between the potential outcome from program D and the potential outcome in situation when those individuals would not go to the program. Now, this parameter of interest is great when we would like to assess a program that would be fully deployed on the whole population of individuals. But typically, we do not send all the unemployed people to one program globally. We assign individuals to programs. Therefore, a better parameter of interest in this case is the conditional average treatment effect. And there we can distinguish two cases. In the first case, we condition on X. This brings us to a so-called individualized treatment effect because we can see what we can expect the difference between two potential outcomes to be for an individual with this specific value of features equal to small x. This could be too granular, so sometimes people think about, maybe we should look at the difference in these potential outcomes more on a higher aggregate level in groups. So now we can replace X by a low-dimensional subset of these X features, which here is called Z. And then looking at some particular group, like let's say either male or female, we can then have a look at what we expect the difference between these two potential outcomes to be on a group level. If we look at these quantities, there is an immediate challenge staring at us, which is that in the data that we observe, we never observe these two potential outcomes for one individual. We either observe the potential if the individual didn't go to the program, then we observe the Y0. And if the individual went to the program, we observe the YD. So now how we deal with this situation when we cannot directly see these two outcomes in our data. The way how to go about it is so-called selection on observable frameworks. I don't have time to explain the details, but the selection on observables brings 4 assumptions, and if these 4 assumptions are satisfied, then we are able to produce the following identification result. What does identification mean? Identification means that we are able to rewrite an element that contains random variables that we cannot directly observe into a different entity in which we can observe all the data, and then we can use the data to estimate these entities. So under the 4 assumptions that are under this selection on observable framework, we can now rewrite here the individual average treatment effect into the difference of these 2 expected values that you see on the slide. And now the y is defined as the observed y of the unemployed individual. So the equation below basically captures that once an individual goes to some program D, I will observe this potential outcome yd as this observed y. So now if I look at the identification result in the first bullet point, I'm now facing a regression problem where I just need to figure out how I estimate this expected value of y looking into a group of people that are defined by the x being equal to small x and by the treatment assignment being in D, and the second quantity accordingly looking into the group of people who are defined by x small x and D being 0. I think I'm good. The similar results can be also obtained for the group average treatment effect and the average treatment effect. Now, seeing this result, I just used one of the identification results under the selection on observable just to illustrate the idea of what identification means. But under this concept, there are actually many more identification results for the treatment effects. And some of those identification results are very suitable to be combined with machine learning methods. So let's now have a quick look at some of those methods that are sitting now under this umbrella causal machine learning. So when we use causal machine learning to estimate the individualized average treatment effect, there are 2 options. So one of the identification results leads to the so-called doubly robust score, and this doubly robust score can be estimated by the double machine learning framework introduced in the paper by Jana and others. And once we have these robust scores, we can regress them on the axis, and this yields then the individualized average treatment effect. Alternatively, we can use causal forests, which are specifically tweaked to yield final leaves on which we can then produce results which can then be also used for the estimation of the individualized average treatment effect. So among causal forests, there are 2 methods currently available: the generalized regression forest by APFL and an alternative, the modified causal forest introduced by Lechner and further developed in the second paper. The individualized average treatment effects have a huge advantage that they give us insights on a very granular level into what could be a program from which a certain individual can profit. The effect can also show that this individual has a negative effect from it or a 0 effect. And the eye, it brings us on this very microscopic level of what can happen. The disadvantage is this black box nature, because it kind of works in a way that, oh, please give me your axis, and I'm gonna give you your value, be it positive, 0, or negative. But it doesn't really help to really understand why this value is positive, 0, or negative. That's why shifting the focus to these group average treatment effects might help. So regarding the estimation, there are again 2 options. Again, taking these double robust scores, which now can be constructed again by the double machine learning or the results coming from the generalized random forest. And then they are regressed on these group variables producing the gates. Or alternatively, one can take these individualized average treatment effects for the unemployed people in the specific group and just average them up to the gate, which is the idea implemented in the modified causal forest. What is the advantage? Now it brings a little bit easier interpretability in the sense that now we can look at the differences among groups. So in this example, I just took a group of male and a group of female, and now looking at the differences in these estimated potential outcomes might start indicating that there might be something behind what works better for male or female. Well, there is a price to pay for this little advantage, and the big disadvantage is that these results are prone to be contaminated by correlation of, in this case, gender with other variables. So if you would assume that maybe gender is highly correlated with the level of education, and it's actually level of education that's driving different results on the labor market, then this result with gender would actually just mask the real underlying relation between the treatment effects and the feature of the unemployed individual. So how to deal with this disadvantage? So now the balanced gate comes to the game. So that's a new concept which is introduced in the paper by Berth and Lechner. And what they propose is, well, let's look at these differences between these two gates, but let's start balancing on features that we might think might be highly correlated with our group variable. So then the formula just basically captures that, okay, let's now look at male and female with the same level of education, basically creating this balanced sample where we create identical individuals with except of just one feature. And then just looking at the average differences there, unmasking the potential result that was brought just by correlation between the features. The way how to estimate is, again, either double machine learning way or the causal forest way, and the main goal is just to look at treatment effects accounting for variation in other features. So let's have a look now how it would look in an application. So we do look at the interventions in Switzerland. So this is a project where I'm a part of together with Professor Lechner and another 3 PhD students. We use Swiss administrative data from 2004 till 2018. We look at unemployed individuals eligible for benefits between January 2014 and 2015. We have 5 programs in our data. For the lack of time, I will just show results for the last program, the temporary earnings. And we look at two outcomes, which are probability of employment and level of earnings in the 3rd year after the start of the program. And again, for the lack of time, I'll just show the results for the level of earnings. So regarding the features, thanks to the administrative data, we have a really large collection of socio-demographic characteristics, prior employment history, prior unemployment history, and we also added some macroeconomic indicators like regional unemployment rate. Regarding the method, we go for the modified causal forest, which is available as Python package for the estimation of such treatment effects. Now going to the results, let's have a look at the first gate, where we looked at the sector of previous employment. So the red line captures the average treatment effect. So you can see that average treatment effect from this last program, which was temporary earnings, is slightly positive. The dashed lines measure the precision of the estimation of this effect. And if you look at the blue dots represent the gates, and the intervals, again, the precision of the estimates. Now, if you look, some groups profit more from the intervention, and some groups profit less. So since economists don't like negative effects, we now see here that sector 2, which is the IT sector, and sector 6, which is the banking and law, seem to have negative effects from going into this program on their level of employment 3 years after. Now, is this something that we can now link the sector to the different treatment effects? Well, let's start balancing. Let's now start balancing the individuals that we just we start balancing on things like gender, level of education, and so on and so forth to see if this stays. Well, after balancing, we see that the effects are gone. So this is an indication that the sector of the previous employment was just highly correlated with some other variable, and it just looked that there is some connection between the sector and the treatment effects. Now let's continue the exploration. We go now to the education. So now we have 6 different levels of educational levels, starting from compulsory schooling, going over secondary vocational until the PhD level. And now we see again, so from this particular treatment, the lower educated people seem to profit more than higher educated people. Now again, the same question. Is it just a mask for being correlated with some other variable, or if we start matching or balancing the people also based that we have the same level of education for men, the sector of previous unemployment and so forth, will it stay? Well, even after the balancing, here the pattern stays. So this is an indication that we can indeed make an association between the level of education and different treatment levels. So with that, I'll just conclude that causal machine learning enables estimation of these super interesting treatment effects on individual and group levels, helping us to produce more granular predictions, better indications, and the balanced gate seems to be the tool how to account for correlations between features.
Many thanks to Jana. Time for questions. We have only one question, I think. Yeah, one question. Yes, please. Time. Yeah.
The term causality, is this meant in the Pearl's causality sense? So causality, is this related to the notion of pearls?
Yes.
Pearl?
Yes.
Okay.
That it's really like going to the program really causally affects the outcome variable.
Okay, thanks.
Yes. Mm-hmm.